Yeah, thank you, Avi. Good afternoon, everyone. Let me start my talk. I'm Gwee from NTU, and then today's of my talk is on the machine learning for circuit extraction based on IC images. So let me present to you the outline of today's talk. I'm going to give you an introduction of the so-called purpose of our project. Also, I will review the reported techniques on this circuit analysis. I'll go into the deep learning in our IC image analysis. I'll present to you the machine learning and feature extraction of our this circuit analysis part. And I'll present to you the visualization and I'll conclude my presentation. So let me go through the introduction with you. The purpose of this IC extraction is actually have three objectives. The first objective is to protect the intellectual property. It allows us to do a IP infringement investigation through this circuit extraction. Second, we also allow to detect the malicious hardware. For example, if there's the hacker to put in this additional circuit onto our systems. So normally we call it hardware Trojan. So we uncover it. So third is actually to do the power hardware failure analysis through this circuit extraction. So you look at the IC image analysis, it starts from the package IC and then you move on. Let me show you the pointer. So from the package IC, then you go on to the remove the package. And then this step, we usually call it decap of IC. And subsequently, as you know that the IC usually have 12 layers or even more from the substrate polysilicon all the way to metal 1, metal 2, metal 3, metal 4, all the way to metal 10. So you need to delayer it. After delayer it, then we need to take the images. For this imaging, we can do the scanning, electron microscopic, or you can do the optical microscopic. So after you take out all the pictures, then you can proceed with the IC image analysis. In here, which I'm going to detail later, this part it involves image stitching, object identification, as well as stacking. Then subsequently, you can go to identify the schematic analysis, identify the circuit function, circuit structure. So let me go into detail. In here, the IC image analysis is a key step of this IC circuit extraction. So let me introduce to you the delayer IC image. On the left-hand side here, you can see that it is an example of 10 layers, the layer sample of circuit images. It starts with the bottom layer, which is the thinnest, the substrate, polysilicon, metal 1, metal 2, and all the way to metal 10. So the typical image size for the SEM machine to take is 1536 times 2048 pixels. This means that you take the small images of this size. Then in the particular layer, how many images will it be? It will be around 200,000 images per layer. This means that if you have 10 layers, you will have around 2 million images. So you can view that the number of images that you have to deal with is a large number, a huge number. And this is a sample image from a poly layer. As you can see here, from poly layer, you can see the polysilicon, you can see the contact, and you can see also the diffusion. So if you look at the tasks, there are basically three main tasks for the IC image analysis. The first task, which is called image stitching. And image stitching and the result evaluation means that after you stitch, you have to evaluate whether your stitch image are well stitched or misaligned. Subsequently, we will go to the feature extraction. The feature extraction, in here we have semantic segmentation and object detection. Semantic segmentation, it means that you identify this pixel, it belongs to the via or belong to the polysilicon or belong to the metal. So there are a lot of images and you have to identify each pixel or each region they belong to which particular components. And object detection means that you have to identify whether this is a transistor, this is the AND gate, OR gate, and so on. After this step, we can proceed to image stacking. You have 10 layers of images, so you stack them together based on their contact point or based on the via. Because all this particular information is actually interlayer. And subsequently, you can generate a next list. So let me give you a simple example. On here, this is a metal layer where it is a vertical metal. Then there are some via on top. Here, second one is also a metal layer, horizontal metal, and there are some via on it. When you come to the third image, it is a polysilicon. And in polysilicon, you have contact. So this contact will contact through this hole to from the polysilicon, and then to form a transistor with the diffusion. Here is also a polysilicon. So you have gate, you have contact, and diffusion and polysilicon. So these are all sample delayer IC images taken by the SAM or optical microscopic from different chips, different layer, and different imaging settings. Let us look at the challenges of this particular IC circuit analysis. First of all, it has large amount of images and it's infeasible for manual analysis. If you look at it, you have different chip technologies. For example, 40 nanometer process, 28 nanometer process, and subsequently 11 nanometer process. And also you have different image settings, SAM, optical, multiple SAM, and so on. And you also have different layer in each chip, substrate, poly, M1, M2, and so on. So this is a large amount of images. Second is that the existing flow are inefficient and require large human intervention. For example, the classical image processing technique are not very reliable. The accuracy is very low, which I'll explain to you later. The chip complexity is increasing, and it is going to be a big problem for us. And also, we require IC expertise. And IC expertise is very expensive, as you know. And also, we have limited number of machine learning approaches. In here, the chip images usually is not open source due to the confidentiality. Because most of manufacturer, you will not show you their so-called chip images. Second is a pixel level labeling for images for every chip layer is time consuming. Here, pixel level labeling, it means that you go to the images, you particularly label this is a via and this is a metal. Okay, let us look at our target. Our target is to develop techniques that are less human dependent. The human involvement should be limited. And in here, we also want to have a technique that are not data hungry. Less data labeling is desired. Techniques that are adaptable. Adaptable in here, we also referring to continuous data labeling for each chip layering, and each image processing, image setting is not acceptable considering the skill. So this means that if you have developed a technique that can use for this particular chip, you also hope that this technique can be used for subsequent new chip. Let me go to the detail, especially I want to explain to you what is the meaning of data labeling. Let me review the reported techniques. There are two conventional approaches for doing this IC image analysis. This is called manual annotation with software assistant. So this means that you have an image, particular IC image like this case. So you need to do a data labeling. You will tell the software that this point is the beginning of the metal, and then you label it and label it again, label it again, label it again, label it again, label it again. So the software will know this is a metal line or metal interconnection. In here, human operator marks key point or images, and software will line up points. Human operator mark region contour, and software will segment out contour. For example, I mark out this one is a transistor, and this is the AND gate, and so on. However, this method is very time consuming and also error prone. The second conventional approach is that template matching using design file. It means that this is an image that we have. We have a template. For example, this particular template is a SRAM cell. Then I will compare this SRAM cell with every part of the image. So human operator will define ideal template for each interested component using design file and scan through the IC image using the design template and try to find a match. After you find a match, you will generate this similarity level. The red color one is for high similarity, the blue color one is for low similarity. And then you, after all, you can actually go and identify the particular template that you're interested, whether they can be found in this particular image. The issue of this technique is that design files are hard to obtain in practice, this design file, and also very time consuming, and is the moderate accuracy. Now we look at a conventional image processing technique. There are three of them, which I'll go through briefly. First is using the threshold algorithm. As we know that the background is darker, and then the VR in this particular case is actually brighter, and metal line is in between. So we define two threshold level. So anything that below the T1 will be background, in between T1 and T2 will be metal line, and above T2 will be VR. However, this technique is low accuracy, susceptible to noise, and image dependent, which I'll show you the example now. If you look at left-hand side, the sample image, if you go through this thresholding algorithm, on the right-hand side, you can find that those brighter spots are supposed to be a blue color or purple color in this case, and then they're supposed to be a VR. But if you look at some noise, these are slightly brighter, and you also identify as the VR. Second image processing technique is actually the shape detection. We can use a circular half transformation. As you know that most of VR are actually circular shape, then you can use this method and then to detect the VR. However, you can find that it is very susceptible to noise, image dependent, and also go for regular shape only. For example, in this case, you can see that here it looks like a circle, and this will be the identified as a VR, but it is a noise. Third image processing technique is a edge-based segmentation. As we know that you detect the edge in the image based on the pixel intensity differences. For example, from this edge to another edge, you know that this is a VR and this is a so-called diffusion. So you can use this method. However, using this method also at low accuracy, susceptible to noise, and also image dependence. Let's look at the reported machine learning. For reported machine learning, there is one technique called unsupervised clustering. So for unsupervised clustering, it clusters the three different group of components, for example, or this object. So the pixel belong to same object tend to have a similar intensity. So you can cluster them and slowly, hopefully you can break them into three different groups. However, the issue is a low accuracy susceptible to noise. So let me move on to our proposed technique, deep learning in IC image analysis. In here, we have presented our work in the International Symposium of Physical and Failure Analysis 2020, and also Digital Signal Processing in 2018. So let me go into the technique in detail. So for the deep learning-based image analysis framework for hardware assurance of digital IC, as you can see that here we have a routing layer which called metal layer, and also have a standard cell layer, which is a polysilicon layer. So the metal layer usually consists of the metal line and the via. We want to identify this so-called we can call it the region or component, and we want to segment them. And also we want to identify the standard cell inside this polysilicon layer. So what is the task? Let me move on here. So the task involves three main tasks. First task is the image staging and result evaluation. Second task, which called feature extraction, semantic segmentation, and object detection. Third is image stacking and netlist generation. I'll go into detail later. If you look at here, the advantages of using the deep learning based method is that it is fast due to inherent leverage of parallel processing using CNN on GPUs. And also learning extraction rule from the large amount of data ensure robust extraction against image noise. So you can continue to learn with the new data. End-to-end training and interference allow realization of complex tasks. So we allow to learn and also that train and subsequently to inference again and train again. So for complex tasks, you have to do it many, many times. The step in realizing DL-based image analysis method. So let me explain to you the steps of what we carry out to design this deep learning-based method. First, we have to select or construct an appropriate model. We call it the DL model architecture. After we selected this model, then we can prepare our training data, a crucial step where automation is highly desirable. And also we train and test the DL model. After that, we can use that model for our identification or analysis. So our contribution, you can look at our contribution. We propose and demonstrate a complete deep learning-based image analysis framework for IC circuit extraction. We also propose and demonstrate various automated and semi-automated training data preparation, which again, I will explain later, and demonstrate effectiveness of using synthetic data to train DL models. So we can use synthetic data which is generated by us. We also implement novel DL model to perform tasks previously done manually, which again, detection of stitching, misalignment, and image stacking. So if you look at this, let me explain to you the image stacking, which include the phase correlation and deep learning-based misalignment detection. If you look at image staging stage, we will use a phase correlation and also do the fully automated deep learning-based to do a synthetic training for the detection of the misalignment. This one I will go into detail later. We also do the feature extraction. Feature extraction is to actually extract the particular feature of a cell in the image. And we also do the segmentation to segmentate for example, the metal line and via. And last but not least, we will do the image stacking. Image stacking, you have 10 layers of images, which each layer is about 200,000 images. Then you have to stack them together. So we are using the custom deep learning regression model. Let me go into detail now. If you look at the staging stage, the staging stage is that we will train the machine learning for identify the misalignment point. For example, in here, there are two images, they stitch them together. After stitch them together, you can see that there's a misalignment here. So we train the machine learning to ensure that he can pick up this misalignment. So the stitching misalignment, our result will be less than 2 pixels will correctly identified by our DL object detection model with high accuracy. So as long as you have a greater than 2 pixel misalignment, you'll be able to pick up. And it is very fast. Fast processing speed, 0.5 seconds to process an image size of 1006 times 1006 on GPU. So second is a standard cell detection. So we use a DL-based standard cell detection to detect this standard cell inside the image with high accuracy. And then also you have a fast processing speed, about 3 seconds, able to process an image size of 10,000 by 10,000 pixels on GPU. Here, we also do the VR and contact segmentation. So we're able to detect the VR and context. So using the DL segmentation model, and then the accuracy is about 97% or greater than 97%, then the processing speed is 4.4 seconds. You're able to do a size of 1024 by 1024. Here is the machine learning technique to detect the metal line, or we call metal line segmentation, with a very high speed and accuracy. So this is to do the image stacking. For image stacking, we use another method. We use a DL regression. Because the output is not just 1 and 0. The output, we want to ensure that there are 2 layers here. For example, one layer is we call it the white color dot, or you call it the VR on the metal layer. And this is on another metal. So you want to ensure that this so-called this VR is stacked nicely onto another layer, which is on the metal line. And if you have any pixel that is actually misaligned by the horizontal or by vertical, then you will be picked up by our machine learning technique, and you will be able to tell you that it is misaligned by vertical positive 3 pixel and horizontal minus 2 pixel. So this is the meaning of regression model. So it is very fast as well. It is a 0.8 second to process an image size of 980 times 980 on GPU. So let me show you the result. I hope you can see the table. So in here, you can see the table, which is a DL model for misalignment, for standard cell detection, for segmentation, metal line segmentation of VR and segment line and stacking model. So we are using the model architecture of faster RCNN, which was developed by the Rose Gershet, and then with the ResNet of 50 backbone, with a training data of 5,000 synthetic training images, and then here you have a training image size of 512 by 512, training epoch of 5, batch size of 20, and we're using the optimizer of SGDM. What is the meaning of that? Let me explain to you. For here, if you have training data of 5,000, we use a batch size of 20. So this means that every batch you have a so-called 250 images, you will do a 1 batch. So after 20 batches, then, after 1 batch of 20, and then you will have a 1 epoch. So this means that you will take in altogether 250 images and as 1 batch, and then 20 as a batch size, you are equal to 1 epoch. And then 5 epoch, you'll be able to train to this particular model. So let's look at the result also. In here, we will find that we achieve a very good result. However, there are some drawback. It is one potential drawback. It is a possible need to retrain the model when applied to new set of images. However, this is the same thing for the this conventional method. A few solutions to elevate this method to do the retraining is that we can use our automation or training data preparation and use a syntactic data training, which I'm going to detail later. Okay, the technique that we use is actually deep learning for automatic IC image analysis. Here we have a design this fully conventional fully convolutional neural network FCN, and here this IC image So this IC image size, as I mentioned to you earlier, it is quite large. It's close to 1000 by 1000. Then you go through the FCN. So here we have a 96 filters. So you have 96 of this image information, and then subsequently 256 channel and so on. At the end of it, you have a ground truth to compare. So this is a forward inferencing and backward learning. So to train the network. So after you train this network, you will realize that this is a step that I'm going to explain to you. After we collected from the same images, then we do an inspection and feature localization. So we identify randomly the sample selection. Means that in a big image, we identify different location for training. And then to do a combined analysis and characterization. For this part, we will need to characterize them whether it is an image with noise, image with systematic noise, or image with irregular noise. So you train it in order to pick up all these noises. And here we also do a data augmentation. Data augmentation means that you have one piece of image. If you flip it, you have two images or two data. Then if you rotate it, you become 8. So from one data, you can generate it to become 8 data. So this will create a lot of synthetic data we have using these steps. And in here, we will do a data training or training the data with the ground truth. And then after provide, then you train the network. After you train the network, then you have a model. With this train model, then you do an evaluation. Usually we use say for example, a thumbs of rule is that, a rule of thumbs is that 70% of training, 30% of testing. So you use a testing, but while you are doing a testing, you find that you don't satisfy with the criteria, then you will add in a new image with a new error, and then to train the data, to train the model again. After you train it, it will improve the accuracy. Okay. So let us take a look of this experiment. So in here, for example, in our model, we are able to train this charging noise. Charging noise in here is actually the line here is not supposed to be here. These are metal line, and then this particular white line is called charging line. And then we also be able to pick up the dust noise, like this case, particular dust noise here and there. The sample VR will be able, via segmentation, will be able to pick up the noise and then separate with the VR. Let us look at the result. So the results show that the false positive per image means that one image you could have a lot of VR. It could be 1,000 VR, not 1,000, it could be a few tens of VR, maybe a 30, 50 VRs. And then could be 100 also. Then your error is actually 0.47 of positive. False positive means that you pick up the VR, but it's not supposed to be a VR. As compared to a conventional image processing technique, it is much higher. And then for the false negative means that it's not supposed to be a VR, but you pick up as a it's supposed to be a VR. Negative means that it's not supposed to be a VR, but you pick up as a VR. Okay. So in this case, 0.02. And then you look at the metal line. Metal line, we have a short circuit error and open circuit error is also very low compared to the conventional technique. So let me show you another machine learning technique and feature extraction that we have proposed. We propose 3 techniques. One is a hybrid k-means clustering and support vector machine for VR and metal line detection. We also propose a hierarchical multi-classifier for automated analysis for delayer images. We also do a global template projection and matching method for training-free analysis for delayer IC images. So let me explain to you now. Hybrid k-means clustering. If you understand hybrid k-means clustering means that k means number of clusters you want to put. Means then that you all cluster into the particular center point. For support vector machine, it is actually trying to identify, trying to classify the 2 different region or 2 different type of items, and then trying to open up the gap. or trying to widen the gap. So in here, this is a SAM images for the metal layer for the layer IC images. This is a VR and this is a metal line. So we're trying to classify the VR in this image and also trying to identify the metal line also. So the object is to retrieve the metal layer interconnection and detect and locate the exact position of VR and precisely segment the metal line. So we use this method. Let me briefly explain to you. You use unsupervised k-means clustering to provide a candidate region for VR and metal line. And also we use the supervised SVM classifier to scan through the candidate region for VR. Okay, let me explain to you. On top is actually for the VR identification. First, we have the original image. Then subsequently, a candidate region. You use the segmentation region candidate VR. So you use a k-mean clustering. K-mean clustering means that you want to cluster VR and non-VR. So after you cluster array, you use the SVM classifier to remain VR region to separate them. Finally, you get a VR position. For the bottom one is actually to identify this metal line. To identify metal line is slightly more difficult. So instead, we identify the background. The background is black color. So we minus away background. So we identify the black color background. In here, if it's not the background, it must be the metal line. So from here, we subtract the background with the original one. And then we can get back the metal line. So we use this hybrid k-means clustering and support vector machine for VR and metal line detection. In our method, we're able to achieve the mean precision on 98.12%. Sorry, our proposed one is 100%. If you compare to the reported circular half transformation is 98.12%. So our mean recall is 99.65%. Our mean F-score is 99.82%, and F-score variation is very low. F-score variation low means that for different images, your consistency is very high in achieving the identification of VR and metal line. So high precision and recall, more robust across different images. So now you look at this other score also, it's very high. Because of time constraint, I'll move on to another technique. This technique is actually a hierarchical multi-classifier system for automated analysis for the layer IC images. So this means that in here, these same images, you have a contact, you have a polyline, your diffusion, your contact on diffusion, your background. So we're trying to identify all these items. So in here, we have a different shape library. Then we use this proposed multi-classifier to classify them, to scan through. And finally, we have this different shape. We created this different shape based on design rules, layout design rules. And then with this library, we scan through the images and then to identify, to locate this polyline, contact, and background. So this is the hierarchical base. So this means this is the background we have. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There are 16 SVM here to do a classification. And here, this is a result. So able to classify the polyline, the contact on polyline, contact on diffusion, and diffusion.
But we
so
have
this is a result.
5 minutes.
Okay, sure.
Yes.
Okay, so let me present the third technique. Third technique is actually the global template prediction and matching method for training-free analysis. So this one don't require training. This one is actually you try the template. Your template is supposed to move, for example, 1,000 pixel here and 1,000 pixel here. It's supposed to move like 1 million pixel, 1,000 by 1,000 to identify all the templates. For our method we have a global matching. This means that we propose a global matching. We have all the template here. For example, the template size is actually 20 by 20. So instead of moving 1,000 point here, 1,000 point, the 20 by 20, you only need to move 19 points on the horizontal and 19 points to the vertical. So in order to achieve this template matching and then to identify the template, the so-called the cell in the image. So this only requires 381 moves instead of 1 million moves. Okay, so these are the equations which I will not go into detail. Okay, let me show you the result. The result is our template, proposed template-based this technique is actually, it requires no training, and then it has a reasonable, not very high accuracy as compared to the deep learning as well as our earlier proposed technique, but it is actually very fast. So this is an advantage of this technique. Okay, let me show you the video on deep learning-based circuit analysis for digital IC. So give you an idea of what is the entire presentation I have earlier. So let's take a look at the video. Okay, let me finish the presentation. Okay, the visualization, what we want to do is actually we have a different library cell, and then we want to use the library cell to match the new images. So if they match, then we can straight away can use a new library, the library cell to do a training, so that it will be very effective. The other method is actually we try to through the neural network or this CNN network, so that there is no ground truth for the new image. We still can fool them by tweaking this model. There are few methods we can propose also. Okay, conclusion. I think we have presented all this. And now this is a publication. And also now come to the question and answer.
Thank you very much. Actually, there are only two questions right now. One is how do you prepare the synthetic training data? Is there no standard in how you label them? You
So,
can look also on the Q&A part. So the question is, you mentioned the synthetic data, how you
yeah,
prepare the synthetic data and how you label if there are no standard, or at least this is the assumption.
yeah, good question, Avi. So you look at the synthetic data in here. What we can do is actually there are a few ways. One way is this you can generate using the design rule, and you can generate using the this synthetic data where you know that your horizontal line is either horizontal, metal line is either horizontal or vertical or diagonal. So you self create this data, and then you put into the training, so-called to train the network. The reason we want to use this synthetic data instead of actual data is in actual data, you may be very noisy. And secondly, in actual data, they may not be so ideal that what we are trying to identify. So this is a synthetic data. And then semi-automated means that we can actually train it a few times. If we find that it cannot identify a particular image, then we can take in the particular image to train the and also
Okay, thank you. A last question, and can these techniques also be used for counterfeit detection?
sorry, can you repeat again?
Can these techniques also be used for counterfeit IC detection?
For what? IC detection?
Yeah.
For detecting counterfeit ICs.
Oh, counterfeit IC, yeah. Okay. If you want to use a counterfeit IC detection, we are using the template matching. And then we are trying to identify if we can actually locate this template in here. You can see that we are trying to find if there is any, for example, this is an image given to us. We are trying to look at the particular image, whether this is actually from the template, whether you can find in the actual image, or from the image there you identify this template, whether there are any other part they have a same uh, component. So in here, by using this method, you still need IC expertise, but again, they will cut out a lot of time in doing this counterfeit IC. Yeah.
Thank you.
Thank you.
I also have one question, Gwee. So basically, like if we take the whole process end to end, how does like the effort or the success changes when we go from an old technology to a new, smaller technology?
Go for old technology to the new technology, the main challenge is actually the image preparation. So if you look at the earlier part when I present to you earlier in the image preparation, if you look at all these images they present to us, if the image is actually able to be able to use by our tools, then we are very, very confident that it can be a very high accuracy. That means that these images, if your process technology going down, it will affect the image taking, but it's not so much affect our side, the circuit analysis part.
Okay, thank you very
Yeah.
much.